Okay, let's unpack this. Imagine you're staring down a problem, right?
Mm-hmm.
Maybe one where you need to find like the best possible way to do something, the cheapest route maybe.
Or the fastest schedule, maximum profit, something like that, yeah.
Exactly. And instead of getting, bogged down in all the complex calculations or mapping out every single possibility,
Mm-hmm.
you think, what's the easiest, most obvious, best step I can take right now?
Just right now.
Yeah. You just grab what looks like the absolute best option in that instant. You don't worry too much about like the history of how you got there or all the ripple effects way down the line.
Right, that immediate, almost self-interested approach.
Yeah. That take the best thing available now mindset. That's
Mhm.
that's the core idea we're diving into today.
And that core idea brings us to, well, a really fascinating class of algorithms known as greedy algorithms.
Greedy algorithms.
Okay. These are pretty powerful tools in computer science,
Okay.
especially for tackling what we call optimization problems.
Optimization problems.
Right.
Right, where the goal is finding the absolute best solution, maximizing something, minimizing something else.
Exactly. Finding the best among a whole set of possibilities.
Got it. And for this deep dive, our guide, the source we're using, is an excerpt from Hello Elgo.
That's right. Chapter 15.1 specifically. It gives a really clear, fundamental look at the principles, what makes these algorithms tick.
Okay, good. So, what's our mission here? What do we want you, the listener, to take away?
Well, our goal is to equip you with a really robust understanding of greedy algorithms, something that, truly sticks with you.
More than just a definition.
Definitely. We want to go beyond that. We'll explore the fundamental concepts, see exactly how they operate with examples, appreciate their strengths because they do have them, but also, crucially, understand their limitations.
And see where they're actually used.
Yeah, look at where they're commonly applied in the real world. Think of
Yeah.
it like building a solid foundation of knowledge about greedy algorithms that you can, rely on.
Absolutely. And we're here to guide you through this material. We've sifted through the source, pulled out the key nuggets, the insights, the connections, basically trying to make this clear and memorable.
So let's start right there. That fundamental concept.
Yeah.
What really defines a greedy algorithm at its heart?
The source puts it really nicely, quite concisely, actually. It says, a greedy algorithm fundamentally involves making the seemingly best choice at each decision-making stage of the problem.
Okay, that phrase, seemingly best choice, that feels really important.
It is.
It totally captures the essence, right? You're not trying to figure out the whole sequence of choices over time that leads to the best outcome.
No.
You're focused purely on the immediate present. Like right now, at this decision point, what option gives the biggest immediate benefit? Or just looks the most optimal right then?
Yeah, it's all about greedily making locally optimal decisions. Picking the choice that looks best from where you stand right now. The one that gives you the biggest payoff in this moment.
And the hope, or maybe the assumption.
Yeah, the hope, the core assumption is that by always picking the best local option, this series of, well, kind of short-sighted best choices will somehow magically add up.
Magically combined to produce the best global solution for the whole problem.
It sounds quite elegant, doesn't it? Simple, hopeful even.
It is, and that simplicity, well, that's a huge part of their appeal. The source points out their key characteristics. They're concise, efficient, and widely used in practical problems.
Concise, efficient, widely used. Okay.
When a problem's structure actually fits the greedy approach, you can often find a solution with way less computational effort.
And simpler code.
Yeah, much simpler code compared to other methods.
That ease of implementation and the potential speed gain, that
Yeah.
sounds incredibly attractive. It feels much more straightforward, right? To code something that just looks at the immediate step.
Totally. Much easier than something that has to consider all these intricate dependencies or explore massive decision trees.
Right.
And this is where the source brings in a really critical comparison. It compares greedy algorithms with dynamic programming, or DP.
Ah, okay. Dynamic programming. My gut feeling for that is building up solutions from smaller pieces, remembering past results so you don't have to recalculate things.
Exactly. It feels more structured, maybe more thorough than this immediate best choice idea.
Yeah.
You're already picking up on the key difference. But first, the similarity, which the source points out. Both approaches often apply to problems that have something called optimal substructure.
Optimal substructure. Okay, what's that again?
It basically means that the optimal solution to the overall problem can be built by combining optimal solutions to its smaller subproblems.
Ah, okay. Like building something complex, the best way to build the whole thing involves building each smaller part in the best possible way.
Precisely. And both DP and greedy algorithms can leverage this property when it exists.
Okay, so optimal substructure is like a shared foundation. But where do they really diverge? What's the big difference?
Okay, here's the critical distinction the source highlights. Dynamic programming, it's more comprehensive. When DP is at a decision stage, it considers all previous decisions and uses solutions to pass subproblems to construct solutions for the current subproblem.
So it remembers stuff. It has a memory, a history it looks back at.
Exactly. It uses that history to make the current best decision in a fully informed way. It explores potentially a much wider set of possibilities based on past results.
Gotcha. DP has a memory. So greedy.
Greedy, by contrast, the source says, does not consider past decisions. It's like it lives in this perpetual present moment.
No looking back.
Nope, it just proceeds with greedy choices, continually narrowing the scope of the problem until it is solved. It makes its single, immediate best choice, commits to it.
And that choice simplifies the problem somehow.
Right. It reduces the problem, letting the algorithm move on to the next immediate best choice in the now smaller, modified problem. It's very single-minded, just moves forward.
It definitely sounds simpler to implement, like taking the most promising step forward without glancing back or trying to peek too far ahead.
It generally is simpler in its logic and often in its code.
Yeah.
Which, like we said, is a big plus.
Okay, so to make this more concrete
Yeah.
and maybe show the downside, the source uses an example.
Yes, a classic problem, the coin change problem.
Yeah, okay. I think I know this one. You have a set of coin types, right? Like pennies, nickels, dimes, quarters.
Right, denominations, say 1, 5, 10, 25 cents.
And a target amount, like, I don't know, 78 cents.
Yep, and you have an unlimited supply of each coin type. The goal is to find the minimum number of coins needed to make exactly that target amount.
Minimum number of coins, okay.
So the source describes a very intuitive, greedy strategy for this. It says, given the target amount, we greedily choose the coin that is closest to and not greater than it, repeatedly following this step until the target amount is met.
Okay, closest to and not greater than. Let's try that with 78 cents and our standard U.S. coins. 1, 5, 10, 25.
Go for it.
All right, target is 78. Largest coin not bigger than 78 is 25. So take 125, remaining amount. 78 minus 25 is 53.
Okay.
Now target is 53. Largest coin not bigger is 25 again. Take another 25, remaining. 53 minus 25 is 28.
Still going.
Target 28. Largest coin not bigger, still 25. Take a third, 25, remaining. 28 minus 25 is 3.
Okay.
Target 3. Largest coin not bigger than 3 is 1.
Okay.
Take another 1, remaining. 3 minus 1 is 2.
Mm-hmm.
Target 2. Largest coin not bigger is 1 again. Take another 1, remaining. 2 minus 1 is 1.
Almost there.
Target 1. Largest coin not bigger is 1. Take the last 1, remaining. 1 minus 1 is 0. Done.
Okay, so how many coins did that greedy strategy use?
Let's see, 3 25s and then 3 1s. That's 6 coins total.
Right, and for standard U.S. coin denominations, this greedy strategy actually works perfectly. It does give you the minimum number of coins for any amount.
Oh, interesting. So it is optimal in that case.
It is, and when you look at the code to implement this, the source notes, it's so clean,
Yeah.
about 10 lines of code.
Wow, yeah. That simplicity, that brevity in the code, that really highlights one of the main appeals, doesn't it? Easy to turn into a program.
Absolutely, it feels intuitive. Just grab the biggest coin you can first.
Yeah.
And for cases like standard U.S. currency, that intuition holds up. The greedy strategy gives the optimal solution.
But
Mm-hmm.
I sense a but coming.
There's always a but. This is the critical point the source emphasizes. This example also perfectly illustrates the primary limitation of greedy algorithms. That intuitive, locally optimal choice. It doesn't always lead to the globally optimal solution for all possible scenarios of the same problem type.
Okay, so let's dig into that. The advantages and maybe more importantly, the limitations. We touched on simplicity, easy implementation.
Yeah.
What about efficiency?
Right. The source really stresses this. Greedy algorithms are not only straightforward and simple to implement, but they're also usually very efficient.
How efficient? Let's go back to that coin change example.
Okay. Think about the process.
Yeah.
If your smallest coin available is, let's call it min coins.
Like a penny, value 1.
Right. When you're repeatedly picking the largest valid coin, In the worst possible case, you might end up using a lot of that smallest coin.
Right. If you had like 4 cents left and only pennies.
Exactly. But even then, the loop where you make the choices runs at most about times. Where is the target amount?
Okay, so the time complexity, the sort of measure of how long it takes, is something like coding coins for this greedy coin change.
That's it.
That seems pretty quick, especially if your smallest coin isn't, incredibly tiny compared to the amount.
It generally is quite fast, and the source draws a direct comparison here with the dynamic programming solution for the general coin change problem.
Okay, how does DP compare?
The DP approach, which can handle any set of coin denominations correctly, typically has a time complexity of own times amp.
Own times is the number of different coin types, and amped is the target amount.
Correct.
Ah, okay, I see the difference now.
Abschnia is ownna times amp. Yeah, that n factor in the DP solution can make a huge difference if you have lots of different coin types.
So even if an n coins is large, if also large, n times could be much, much larger.
Exactly. The greedy approach, when it works, can be significantly faster. The source even uses the phrase order of magnitude smaller for the time complexity difference.
Which in computing means potentially way, way faster for big inputs, right?
Absolutely. Thousands, millions, maybe billions of times faster. This efficiency is really the driving force behind using greedy algorithms when they're applicable and correct.
Okay, when they're correct. That seems to be the big caveat.
It is. The major drawback, as the source clearly states, is that for some combinations of coin denominations, greedy algorithms cannot find the optimal solution.
It's not a guarantee.
Right.
And the source has examples of this failure in figure 15-2.
Yes, crucial examples that really illustrate the problem vividly.
Let's see.
Okay, first, the source confirms the positive case we discussed. For coins like 1, 5, 10, 20, 50, 100 common denominations, the greedy algorithm does find the optimal solution for any amount.
Good. So it proves it can work perfectly sometimes. The issue isn't that it never works.
Right. It's not guaranteed for every possible setup. Now look at the first negative example. Coins are 1, 20, 50, and the target amount is 60.
Okay, 1, 20, 50, target 60. Let's trace the greedy strategy again.
Go ahead.
Target 60. Largest coin not 60 is 50. Take 150 remaining. 60, 50 equals 10.
Okay.
Target 10, largest coin not 10. Well, 20 is too big, 50 is too big, so it has to be 1.
Right.
So take 1, 1, remaining 9. Take another 1, remaining 8.
Oh, I need 10 ones to make up that remaining 10.
Exactly. So the greedy solution uses 1 50-cent coin and 10 1-cent coins.
Total coins, 1 plus 10 gives 11 coins.
11 coins to make 60 cents with 1, 20, 50.
Yeah, that feels really inefficient just saying it.
It is. The source tells us the actual optimal solution here.
What is it?
It's 20 plus 20 plus 20. Just the 3 20-cent coins. Wow. 3 coins versus 11.
A dynamic programming algorithm would find that 3-coin solution, but the greedy approach, dramatically worse.
Why did it fail so badly?
That initial locally best choice, grabbing the 50, it kind of trapped the greedy algorithm. It put it in a situation where the remaining amount, 10, could only be made using the least efficient coin available, the 1-cent coin. It didn't foresee that taking smaller coins initially, the 20s, would have been better overall.
Okay, that one example makes the potential failure really clear. What's the second example?
The second one, it's even more striking, I think. Coins are 149.50, and the target amount is 98.
149.50, target 98. Okay, greedy approach. Largest coin, not 98, is 50. Take 150. Remaining 98.50 equals 48.
Right.
Target 48. Largest coin, not 48. Wow. 49 is too big. 50 is too big. It has to be 1 again.
So
I need 48 1-cent coins to make up that remaining 48.
Which means the greedy solution uses 1 50-cent coin and 48 1-cent coins.
Total. 1 plus 48 equals 49 coins.
49 coins to make 98 cents.
That's terrible. What's the actual optimal solution?
The source reveals it's simply 49 plus 49, just 2 coins. 2 49-cent coins.
2 coins versus 49. Ouch.
Again, the greedy choice, taking the 50 first because it was the largest single coin, less than 98, it completely missed the much better global solution. It couldn't see that 2 slightly smaller specific coins were a perfect fit.
These examples just hammer it home, don't they? Making the best choice now gives you absolutely no guarantee you haven't messed things up for the overall best outcome later.
That's the core problem. The greedy choice can lead you down a blind alley.
So based on these failures, what's the conclusion from the source about coin change?
The source concludes that for the general coin change problem, where the denominations can be anything, greedy algorithms cannot guarantee finding the globally optimal solution, and they might find a very poor solution.
Which is why dynamic programming is often preferred for the general case.
Exactly. DP is better suited because its more exhaustive approach, building solutions from valid subproblems, does guarantee optimality. It comes at a cost, usually higher computational time, but you get the correct answer.
Okay. So coin change is this perfect case study. Sometimes greedy is great, fast, and optimal, and sometimes it's spectacularly wrong.
Precisely. Which leads us to understand the situations where greedy algorithms are actually appropriate. The source puts them into two main categories.
What are they?
Okay, category one is the ideal scenario. Problems where the greedy algorithm is guaranteed to find the optimal solution.
Like the US coin system or maybe some other problems we'll see.
Exactly. For these specific problem types, because greedy is so simple and efficient compared to, say, backtracking, which explores everything, or DP, which builds tables, it's often the absolute best choice. You get correctness and speed, the holy grail.
Makes sense. What's category two?
Category 2 acknowledges a practical reality for many really complex problems. It's when greedy algorithms can find a near-optimal solution.
Near optimal. So not perfect, but close.
Right. Think about huge, real-world problems where finding the absolute mathematically proven global optimum is just computationally infeasible. It might take years, even centuries, on the fastest computers.
Okay. Yeah, some problems are just too big.
In those cases, a high-efficiency suboptimal solution found by a greedy algorithm can be, as the source puts it, very commendable.
So it's not the perfect answer, but it's a good answer found really quickly.
Exactly. And often, that's perfectly acceptable, even highly valuable in practice.
That's a crucial point. Sometimes the goal isn't find the absolute mathematical best. It's more like find a really good answer fast enough to be useful.
Think about routing internet traffic like you mentioned earlier. You need a path right now, not the absolutely perfect path calculated over the next hour. A greedy-like approach might give you a very efficient, maybe 99% optimal route almost instantly.
And that's way better than waiting for the 100% optimal route that arrives too late.
Precisely. Practical constraints often make the near-optimal but fast, greedy solution more valuable than a perfect but way too slow solution from a more complex method.
Okay. But if you do need that guaranteed optimal solution, how do you know if your problem falls into category one? This must depend on the problem having specific characteristics, right?
Yes. And the source points out that compared to DP, greedy algorithms have stricter conditions they need to meet for guaranteed optimality. It focuses on two main properties.
What's the first one?
The first, and this is really the defining one for greedy, is the greedy choice property.
Greedy choice property.
Okay. This is the strict condition that, quoting the source again, only when the locally optimal choice can always lead to a globally optimal solution can a greedy algorithm guarantee optimality.
Always lead to. That word always is doing a lot of work there, isn't it?
It really is. It means no matter what state the problem is in, no matter the specific input values you have, making the greedy choice in that moment must never block you from reaching the overall best possible outcome for the entire problem.
Never prevent the global optimum.
Exactly. And, well, this is why proving this property is usually the hard part. The source says, in practice, proving the greedy choice property for many problems is not easy.
I can see why. You have to show it holds true universally for all possible scenarios, not just the ones you test.
Right. With our failing coin examples, 1, 20, 50 for 60, or 1, 49, 50 for 98, we could easily show that picking the 50 first didn't lead to the global optimum in those specific cases.
Yeah, finding a counterexample is one thing.
But proving the greedy choice property means showing that such a failure can never happen for any amount, using any starting configuration for that specific problem setup, like a given set of coins. It requires a much more rigorous mathematical demonstration.
So how do people usually prove it?
Often involves techniques like proof by induction or proof by contradiction. You assume the greedy choice doesn't lead to the optimum, and then show that this assumption leads to some kind of logical impossibility. Therefore, the greedy choice must lead to the optimum.
It's complex.
It can be. The source uses coin change again to highlight this, finding counterexamples like we did. Relatively easy. But proving the conditions under which a specific set of coins will allow the greedy algorithm to work optimally for any amount, that's much more challenging. It's a deeper mathematical question about the relationships between the coin values.
So it's easy to poke holes, much harder to prove it's watertight.
Exactly. And just to underscore how non-trivial this can be, the source mentions a research paper
Oh, yeah.
from 2005. It developed an algorithm specifically just to determine if a given set of coin denominations allows the standard greedy algorithm to find the optimal solution for any target amount.
An algorithm to check if the simple greedy algorithm works.
Yes, and the time complexity of that checking algorithm was a whole where kin is the number of coin types.
Whoa, just to figure out if the simple greedy strategy is always optimal for those coins.
Right. It shows that verifying the greedy choice property isn't some quick check. It can be a complex computational problem in itself, requiring deep analysis of how the denominations interact.
That's fascinating. It really highlights that the simplicity of the greedy execution hides potential complexity, improving its correctness.
Absolutely. So that's the greedy choice property, the big hurdle. What's the second property you mentioned?
The second property needed for guaranteed optimality, which we touched on earlier when comparing with DP, is optimal substructure.
Right. Defined as the optimal solution to the overall problem contains within it the optimal solutions to its subproblems.
And the source mentioned this was covered more in the DP chapter. How does it specifically relate to greedy?
Well, the intuition is that if a problem has optimal substructure, when you make a greedy choice that reduces the problem to a smaller version, a subproblem, that remaining subproblem also needs to have an optimal solution that fits within the overall optimal structure.
Okay. If the big solution isn't built from optimal small solutions, then a method like greedy, which works step by step on subproblems, probably won't find the overall optimum.
That's the general idea. However, the source adds an important caveat here. It says, some problems do not have an obvious optimal substructure, but can still be solved using greedy algorithms.
Oh. So it's not as strict a requirement as the greedy choice property.
It seems that way. Optimal substructure is often present when greedy works optimally, but its presence or absence isn't quite as defining for guaranteeing greedy optimality as the strict greedy choice property is. That property is really the key gatekeeper.
Okay, got it. Greedy choice property is the critical one. Your immediate best step must always be compatible with the overall best path, and proving that is tough. So if you're tackling a new problem and you think a greedy approach might work, what's the process? The source outlines 3 general steps.
Right. Step 1 is pretty standard for any algorithm design, problem analysis.
Understand the problem first.
Exactly. Sort out and understand the characteristics. State definition, optimization objectives, constraints, etc. What are the inputs? What are you maximizing or minimizing? What are the rules? This is foundational, same as if you were considering backtracking or DP.
Makes sense. Can't solve it if you don't know what it is or what solved means.
Step 2 is the core step, according to the source. Determine the greedy strategy.
Ah, this is where you figure out what greedy choice to make.
Precisely. This is where the creativity and potentially the errors come in. You have to devise that specific rule, that heuristic, for making the seemingly best choice at each step.
What's the goal of the strategy?
The purpose is to reduce the scale of the problem at each step and eventually solve the entire problem. For coin change, the strategy was take the largest coin not exceeding the remainder. For other problems, it might be totally different.
How do you come up with one? It feels like the trickiest part.
It absolutely can be. And the source acknowledges this difficulty. It says greedy strategies vary greatly between problems. There's no single formula.
So it depends on the specific problem.
Heavily. For simple problems, the strategy might seem obvious. But for complex ones, finding the right greedy strategy can be very elusive. This is where, as the source puts it, your experience and algorithmic capability, your knack for seeing patterns really get tested.
So it takes some intuition, maybe some trial and error.
Often, yes. And adding to that challenge, the source warns that some greedy strategies are quite misleading.
Misleading? How so?
You might devise a strategy that sounds perfectly logical, like our take the largest coin strategy seemed logical for all coin sets initially, but it might only be partially correct.
It works for some cases, but not others.
Exactly. You code it, test it on a few simple cases, looks good, but then you hit an edge case like our 60 cents with 1/20/50, and bam, your good strategy falls apart, gives a terrible result.
Right. You'd only find that through testing, potentially.
Or debugging. It can be a frustrating cycle. Design, code, test, fail, rethink the strategy, try again.
That really highlights the risk. An intuitive greedy strategy might seem right, but hide critical flaws, which leads directly to the third step, I assume.
It does. Step 3 is proof of correctness.
if you want to be sure it always works.
Yes, to be truly confident that your greedy algorithm finds the optimal solution universally, the source says it's usually necessary to prove that the problem satisfies both the greedy choice property and optimal substructure.
And we already established, especially for the greedy choice property, that this proof may not be an easy task.
Indeed, often requires formal math, induction, contradiction proofs. For many complex real-world problems, getting that rigorous proof might be impractical or require significant academic effort, like that coin-checking algorithm suggested.
So if you're working on something practical and a full mathematical proof is just too hard or takes too long, what's the alternative? What does the source suggest?
It offers a pragmatic approach. Debug the code based on test cases, modifying and verifying the greedy strategy step by step.
So rely on thorough testing.
Basically, yes, it's common practice. Design your strategy, implement it, then hammer it with tests. Lots of different inputs, edge cases, known tricky scenarios. If a test fails, you analyze why the greedy choice led to a wrong answer in that specific instance.
And then you either refine the strategy or maybe you just have to conclude
That a purely greedy approach isn't guaranteed to be optimal for this particular problem. Maybe it's only near optimal, or maybe you need a different approach like DP entirely.
So testing doesn't give the same mathematical guarantee as a proof for all possible inputs.
No, it can't. But it's often necessary and gives you a certain level of confidence for practical applications.
Okay, so the process is analyze the problem, devise a plausible greedy strategy using intuition, experience, and then either prove it mathematically if you need that absolute guarantee and can manage it, or test it rigorously to gain confidence while accepting it might be near optimal or even fail sometimes.
That sums up the general workflow quite well. And despite these challenges in proving universal correctness, greedy algorithms are still incredibly valuable. They're widely applied to many typical problems where those crucial properties do actually hold, or where a near-optimal fast solution is good enough.
Right. Let's talk about some of those typical problems where greedy really shines. We've beaten the coin change example to death, noting it works sometimes but not always. What are some other classic examples where greedy is the way to go?
Okay, a really classic one is the interval scheduling problem.
Interval scheduling, what's the setup?
Imagine you have a list of activities or tasks. Each task has a specific start time and a specific end time and interval. You have a single resource, maybe a meeting room or just yourself, and you can only do one task at a time. The goal is to select the largest possible number of tasks you can complete without any of them overlapping.
Okay, maximize the number of completed, non-overlapping tasks. How does greedy solve this?
The standard and provably optimal greedy strategy here is highlighted by the source. First, you sort all the tasks based on their finish times, from earliest finish time to latest.
Sort by finish time.
Okay. Then, you iterate through the sorted tasks. You select the first task, the one that finishes earliest overall. Then you scan forward, skipping any tasks that start before the first one finished, and you select the next task you encounter that is compatible, doesn't overlap. You repeat this. Always select the earliest finishing compatible task among the remaining ones.
So pick the one that finishes earliest, then find the next one that starts after the first one finishes, and among those compatible ones, again, pick the one that finishes earliest.
Exactly. Always choose the task that ends the earliest among the compatible options at each step.
And why does that work? Why does that guarantee the maximum number of tasks?
It's actually quite intuitive when you think about it. By picking the task that finishes earliest, you're freeing up your resource, the room, or yourself as quickly as possible.
Ah, right. Leaving more time available for potential future tasks.
Precisely. It maximizes the remaining time window for scheduling subsequent tasks. This locally optimal choice getting done quickly directly contributes to the global optimum of fitting in the maximum possible number of tasks. The source confirms this greedy approach does achieve the optimal solution.
That's a great example. The local best, finish fast, leads to the global best, most tasks. What's another one?
Okay, how about the fractional knapsack problem?
Knapsack, like pack in a bag.
Exactly. It's a variation of the classic knapsack problem. You have a knapsack, it has a maximum weight capacity. You also have a set of items. Each item has a certain weight, and importantly, a certain value.
Goal is to maximize the total value of stuff in the knapsack without exceeding the weight limit.
Yes. Now, the crucial difference in the fractional version is that you're allowed to take portions or fractions of items. You don't have to take the whole thing or leave it.
Ah, okay. You can cut items up. So what's the greedy strategy here?
The source specifies the strategy. Always choose the item with the highest value-to-weight ratio. Value weight.
Value to weight ratio,
Yeah.
like dollars per pound or points per kilogram.
Yeah.
Calculate the value density for everything.
Exactly. Calculate that ratio for every item. Then you sort the items based on this ratio from highest density to lowest.
And then just start packing.
Yeah. Start putting the items with the highest value density into your knapsack first. Keep adding them until you hit an item that won't fit entirely.
And because it's fractional.
You just take as much of that last item as you can fit to fill the knapsack right up to its weight capacity.
Okay, why does this greedy strategy guarantee the maximum total value?
Because you can take fractions. Since you can break items apart, grabbing the highest density stuff first ensures you're getting the absolute most bang for your buck, value for your weight at every step. Taking even a small fraction of a super high density item is always better than using that same weight capacity on any amount of a lower density item. The density is uniform throughout the item, and there's no penalty for splitting.
Makes sense. The ability to take fractions is key.
It is. The source notes this achieves the optimal solution in some cases, and fractional knapsack is a prime example where this simple, greedy density strategy works perfectly. It's important to contrast this with the 0-1 knapsack problem, where you can't take fractions, you must take an item whole or not at all. That version is much harder and typically requires dynamic programming, not a simple greedy approach.
Got it. Fractional greedy works. 0-1-1 needs DP. What else is on the typical problems list?
The source lists the stock trading problem.
Making money in the market.
Sort of. Given a history of stock prices over time, the goal is to maximize your profit by buying low and selling high. The constraint mentioned is that you have to sell any shares you currently hold before you can buy again. But you can make multiple transactions, buy, sell, buy, sell.
Okay, multiple trades allowed. What's the greedy play here? The source doesn't detail it.
Not in this section, no. It just lists it as a typical problem-solvable greedily.
Okay. Well, a common greedy approach for a version of this problem is to look at the price changes day by day. If the price goes up from day 1 to day 2, you sort of buy on day 1 and sell on day 2, capturing that profit. If it goes up again from day 2 to day 3, you buy on day 2, sell on day 3.
So you just accumulate all the positive price differences.
Exactly. You essentially take every single opportunity where the price increases from one period to the next. You're greedily capturing every little incremental gain. You don't try to hold out for one big peak. You just grab profit whenever it appears.
That makes sense as a greedy strategy. Each upward tick is a locally optimal chance for profit, and maybe adding all those up gives the global maximum possible profit with unlimited transactions.
Yeah, it's a bit surprising, but it often works for that specific problem formulation. Okay, what's next?
Huffman coding? This one is really practical, used all the time in lossless data compression. Think zip files, things like that.
Data compression. How's that greedy?
Huffman coding works by building a special kind of binary tree called a Huffman tree. This tree assigns variable length codes, sequences of zeros and ones, to input symbols, like letters in a text file.
Variable length, so not all codes are the same number of bits.
Right. The trick is, symbols that appear more frequently in the input get shorter codes, and symbols that appear less frequently get longer codes. This minimizes the total number of bits needed to represent the whole input data.
Okay, less frequent stuff takes more space per symbol, but frequent stuff takes less, leading to overall savings. Where's the greedy part?
The greedy strategy comes in when building this optimal tree. The source says the strategy is to, at each step, always merge the two nodes with the lowest frequency.
Okay, explain that. How does it start?
You start with each unique symbol in your input data as its own separate node, maybe in a list or priority queue. Each node knows its symbol and how many times it appeared, its frequency.
Got it. All symbols with their counts.
Then you find the two nodes in your current set that have the lowest frequencies.
The two least common symbols, or nodes.
Exactly. You take those two nodes, remove them from the set, and create a new parent node. This new parent node doesn't represent a symbol itself. Its frequency is simply the sum of the frequencies of the two children you just merged. You then add this new parent node back into your set.
Okay, so you combine the two rarest things into a new combined node and treat that combination like any other node in the set now.
Precisely. And you just repeat this process. Find the two nodes, which could be original symbols or these new internal parent nodes, with the lowest current frequencies, merge them under a new parent, add the parent back. You keep doing this until everything has been merged together under a single root node, forming the complete Huffman tree.
And why is that greedy process optimal? Why does merging the lowest frequencies first work?
By repeatedly merging the two lowest frequency nodes, the algorithm naturally ensures that symbols with higher frequencies tend to stay separate longer and end up closer to the root of the final tree.
Closer to the root means.
A shorter path from the root to that symbol's leaf node. And the path corresponds to the binary code, so higher frequency symbols get shorter codes.
Ah, because you keep pushing the lowest frequency things deeper into the tree by merging them early.
Exactly. The source states this greedy merging process results in a tree with the minimum weighted path length, coding length, which is precisely the definition of an optimal Huffman code. It's a really elegant example where a simple, repeated local step, merge the two smallest, guarantees a specific global optimum minimum total encoded length.
That is clever. The least valuable things locally, lowest frequency, are dealt with first, and that leads to the most efficient overall structure.
Very cool. Is there one more?
Yes, the final one listed is Dijkstra's algorithm.
Dijkstra's, okay, fundamental graph algorithm. Finding shortest paths, right?
That's the one. It's described as a greedy algorithm for finding the shortest path from a single starting vertex, the source, to all other vertices in a graph. There's a condition, though. The weights on the edges, the costs to travel between nodes, must be non-negative. Right. No negative edge weights for Dijkstra's. Where's the greedy choice in Dijkstra's? I seem to recall it involves picking the closest node somehow.
You're on the right track. The source doesn't detail the steps here, but the core greedy choice is exactly that. Dijkstra's maintains a set of vertices for which the shortest path from the source has already been definitively found. Let's call them visited. It also keeps track of tentative shortest distances for all the unvisited vertices.
Okay, known shortest paths and estimated shortest paths.
At each step of the algorithm, it looks at all the unvisited vertices and it greedily selects the unvisited vertex that currently has the smallest estimated distance from the source.
Always pick the closest unvisited node on the frontier to explore next.
Exactly. You pick that node, declare its current estimated distance as its final shortest distance, and move it to the visited set. Then you update the distance estimates for its unvisited neighbors based on the path through the node you just added.
And why is that greedy choice always picking the seemingly closest node guaranteed to work for non-negative weights?
Because the edge weights are non-negative. If you pick the unvisited node U with the smallest current distance estimate, any other path to U would have to go through some other unvisited node V first. But since V's current distance estimate is already greater than or equal to U's, because U had the smallest, and the path from V to U adds a non-negative weight, any alternative path to U must be longer or equal. So the path you found by greedily picking U must be the shortest.
Ah, the non-negative weights are key. They ensure that paths can only get longer, so once you've found the closest unvisited node, you know you found its absolute shortest path.
Precisely. So that locally optimal choice, expand from the closest node, leads to the globally optimal solution, finding all shortest paths in this case.
Okay, so summarizing these examples, interval scheduling, fractional knapsack, that stock trading idea, Huffman coding, Dijkstra's, these are all significant problems where a specific, often pretty intuitive, greedy strategy really works. It aligns with the problem structure, so the local choices build up to a provably optimal, or, in some cases like stock trading, a desired near-optimal global solution.
Right. They stand as excellent counterpoints to the general coin change failure. They demonstrate that while greedy isn't some magic bullet for all optimization problems, it's incredibly powerful, efficient, and correct for a large and important class of problems. Problems whose structure happens to possess those crucial properties, especially that greedy choice property.
Yeah, this whole deep dive has really clarified the nuance, I think. It's not just about whether a problem looks like you can make a simple choice right now. It's about whether that choice is always the right one to keep you on the path to the ultimate best outcome.
And knowing the difference, or at least having ways to test for it or prove it, that's really the key takeaway.
Definitely. Our aim here was really to provide you, the listener, with that fundamental understanding of greedy algorithms, their power, but also their very real limitations, something you can carry with you.
So let's try to bring it all together. What are the absolute core points?
Right, okay. Greedy algorithms.
Yeah.
Fundamentally characterized by making that seemingly best, locally optimal choice at each decision step.
Right. And their big appeal. Simplicity, usually easy to implement, and often remarkably efficient. Remember that comparison with DP for coin change, potentially orders of magnitude faster.
But and is it the big but Their critical limitation is that this local best choice does not always guarantee the globally optimal solution.
Absolutely critical. Whether it does or not depends entirely on the specific structure of the problem. Does it possess the greedy choice property? That's the main question.
That's strict condition.
Yeah.
The local optimum must always lead towards the global optimum.
And proving that property, as we saw, can be surprisingly difficult. It might need serious math, which leads to rigorous testing being a common practical alternative, though testing doesn't give that same universal guarantee.
Right. So ultimately, the elegance and speed of a greedy solution. Very tempting. But you have to understand if that simple, immediate step is truly aligned with the long-term optimal path for your specific problem.
Sometimes it's perfect, sometimes it's a great practical approximation, fast and good enough, and sometimes, like those coin examples showed us, it can fail quite badly.
This whole understanding kind of offers a fascinating lens to view problem solving through, doesn't it? Not just in code, but maybe even in everyday life.
That's a great point. Consider, a significant decision you've made recently. Maybe choosing a project to work on, planning something complex like a trip, or even just how you tackled a really busy day.
Did you approach it with a greedy mindset? Did you just pick the task or option that seemed easiest or most immediately rewarding right in that moment, without fully mapping out all the long-term consequences?
Or perhaps did you take a more dynamic programming kind of approach? Did you carefully consider all the steps you'd taken so far, how they influenced your current options, and weigh different paths based on their cumulative effect down the line?
How might consciously thinking about whether a situation has the equivalent of that greedy choice property, where the immediate best is the overall best, versus needing a more holistic look-ahead approach, how might that change how you make decisions?
It encourages maybe taking a pause, right? Asking yourself, is this immediate win truly setting me up for the best possible overall outcome here? Or could it be leading me down a path that's actually suboptimal in the long run?
Yeah, it's about recognizing that the simplest, most obvious path isn't always the best path. But, crucially, when it is the best path, taking it greedily can be incredibly efficient and powerful.
Exactly. Definitely some food for thought there. We hope this deep dive into greedy algorithms has given you a really solid grasp of their mechanics, their significant strengths, and just as importantly, their critical limitations, hopefully helping you identify where they can be a fantastic tool and where you need to approach with a bit more caution.